Okay, so everybody, welcome to ABC 190 editorial. So there was a separate video where what a screencast, right? But I decided to separate them so that it's more convenient for you to watch like whatever part you want. If you want like to see how I actually sing during the contest, you can watch the screencast, and if you want editorial, then you can watch editorial, right? So problem A is very primitive game. We have two people who repeatedly eat candies alternatively. The only difficulty is like there's variable C that corresponds to who goes first. And like whoever runs out of candies first, they lose. We therefore always have a winner and want to print the winner actually. So like what I do, I just read the input. If second person, like suppose that somebody goes first, for them to win, they have to have like strictly more candies than the other person. Because if they have equal number of candies, then they will run out of candies first. Then their opponent will run out of candies, and then it's again a turn of the first player and they lose. So I just check that second player got more candies. If they do, then they win. Otherwise, their opponent wins, right? And like otherwise, just reverse the condition. I believe you can do it like in a smarter way, but it worked for me, so I was not thinking long about this problem. In problem B, we have n spells. Each spell has like duration or cooldown and power. But we have a monster that can like avoid taking damage from very long spells. Maybe he can just hide, and he does not. Maybe he got some armor, so he does not take direct damage from spells with small power. So what I do, I just like read the current spell. If spell takes not too long time to cast and is strong enough, then I can just output yes and exit. It's important to, I believe it's important to exit so that you don't print anything twice, but maybe you can go away like with just that, right? Because like if checker only reads one string from input, they will read yes and exit. And if you don't like, the problem asks us to find like any spell that deals damage. So if we find any spell, we can immediately exit. If we don't find any spell, then we just output no. For problem C, balls and dishes, we had like several dishes, several conditions. Conditions were from like both dishes get one or more balls in them. There were several people. People can put, like each person can put either on one dish or on another. We want to like count how many conditions will be satisfied. Now, because k is smaller, less than or equal to 16, we just can iterate over all bit mask encoding people. Like for each person, we say like you put your ball here in this bit mask, and in this bit mask you put your ball there. So that's what I do. I just read input, iterate over bit masks, store best, and I just simulate the process. So I iterate over people again. If the bit is set, then they put like their ball to the second dish. Otherwise, they put it to the first. Then I just iterate over conditions and count like how many conditions are satisfied. And the complexity of that thing is 2 to the power of k times m, which is small enough. 2 to the 16 times 100, I believe it's smaller than 1 million. So yeah, not particularly complicated. And update the answer. Yeah, I was a bit surprised to see like bit masks that's early, but maybe it's okay. But I was still a bit surprised. In problem D, we want to count like how many arithmetic progressions can like so consecutive integers, because difference is 1/2 the given sum. We don't think for long. We say like if our progression is from A to B and the sum is B plus A, because we can pair them with that standard argument, times B minus A plus 1 over 2. This should be equal to n. We can transform it, say like this equals 2n, right? Then here we can write it like this is the sum and this is the difference. So we effectively get what? We get sum times difference plus 1 equals to n. But then it's just very easy because you know that S has to divide to n, and you can look over all divisors of n in quadratic square root time, right? If you do it like this, you look over all small divisors. For all large divisors, you just look over small and generate large divisors. So that was not, that did not took much time either. I'm actually surprised, like, because at the end of the contest, I found out like we were doing like actually pretty badly. So I was really surprised about that. Okay, so that's not important, I guess. Oh, okay. Yeah, so we have like S divides n to n, and we look over S, and like we get the value of d plus 1. And now we have like sum and we have difference, and we want to restore numbers. And it turned out that it's like always possible when sum and difference are the same mod 2, right? Because if sum and difference, so you have a plus b equals s, you have a minus b equals d, actually b minus a, but it does not matter. Then a is s plus d over 2, and b is s minus d over 2. And so you have to, like, s plus d is divisible by, you need it to be divisible by 2, right? To get integers. And then all of these pairs are different because they have different sum. That's exactly what I do. I was actually thinking that I'm doing pretty well up to that point. And we had a magical ornament. And I still was thinking that we're doing pretty well. Let me explain what was going on here. But first, yeah, very good. So here we have several magical gems. For some pairs of gems, we can put them together like adjacent. For some other pairs, we can't. And we are interested in like, we want to our magical ornament to contain given k gems, types of gems. I'm interested in like what is the minimum number of stones that we need to include all of this. And like first thing you realize is this k is small. So if you know like what is the shortest distance to go from Ci to Cj, then you can do a dynamic program over them. Like again, the same thing with bitmask. So we'll have dynamic program and like it's with two state variables. I think state is a pair. First is like who was the last included gem, and the second is what bitmask denoting what gems we already included. So this will work like in 2 to the power of k times k squared. That's okay for k equals 17. And the problem is that like we now want to find like what is actually the distance, what is the cost from going to Ci to Cj, and you can obviously interpret this as a graph. Once you do that, it's like it becomes pretty obvious, I guess, that you want to find like shortest distance in a graph from one vertex to like 16 other vertices, right? But like, how to find shortest distance in a graph? You can just run BFS, right? Because the graph is unweighted. So we run BFS, we compute distances happily, and we like fill our distance matrix among these k-squared pairs, and then we do DP. And then we just want to find like best answer, minimum answer. Like so, one call possible last parts, we can find this. It's like common Voyager, or it's like travel and sales, travel and salesman problem, right? Over k vertices. So first we fill the matrix of distances, then we solve the TSP. So far so good. I actually was doing, I thought that I'm doing pretty well. I don't know what happened, but apparently people find such problems very standard because I was not even commenting a lot, as you probably noticed in my screencast. But like people were much faster. I don't know what happened. I'm really surprised because I saw that these problems are pretty messy now. I'm really good at math. Like pretty much in every problem, I just realized the correct idea straight away. Just implemented it. Almost no time was spent debugging things, so I'm really surprised to see the final result. But anyways, so for problem F, we wanted to count inversions in every cyclic shift of given permutation. So like, suppose that you know how to count a number of inversions in a given permutation. Then what you can do, like, you have to be accurate. What happens when you shift one? Actually, in this notation, you take first element out of the sequence, out of the permutation, and put it at the very big end of the permutation. So that's what happens. So you say like, okay, what happens if I have like permutation? Let me actually go to that example. No, that's a bad example. Okay. Suppose I have such permutation, right? I take one out and put it at the very end. When I take one out, there was one inversion because like one is the second smallest number. There was one number smaller than that, and it was going after it. So if we take AI out, we reduce number of inversions by AI. For the numbers that were smaller and were after. At the same time, there are n-1 minus AI numbers. So in this case, it's 2 and 3, who are greater and were after, but now after we do this, they are before. So we add that many inversions. And the problem remains like, what is the number of inversions in the starting sequence? And that were a weird way because I forgot the algorithm. I would spend like 5 minutes trying to find it in my submissions for different problems because I was confident that it's somewhere there, like the expected algorithm. But I ended up using the power of GCC namely the tree from GNU policy-based data structures. So like it's an ordered set that can quickly return the order of a given key. Suppose you have the power to get the order of a given key. So that's like what place it would end up if you insert it, right? So you can do this. You iterate from left to right. You like ask what is the number of elements who are greater than me in this set, because that's all inversions that happened in the past, right? So you insert and you get like you just count inversions for that element, then you insert and then you return the sum. Unfortunately, I spent like 5 minutes debugging and another 10 minutes of penalties because I was very stupid. I had like integer overflow here. So for some reason, I decided to put answers in a vector to print it like easily later. So I did something like that. So imagine answer being a vector. I take last element because I had like complex logic of modifying it. So I took and I put it into int. And it's really unfortunate because like during the wall contest, I was repeatedly making everything in 64T to avoid overflow, and that is the last problem. I just wasted all that effort, put it into it, got like one overflow, and I thought like this is the order of this operation matches and it didn't match. So I spent another run submission and then only then I got correct answer. So yeah, it was pretty slow, honestly. If you got, yeah, like this is it for the editorial part. If you go to the standings, then I'm not finished earlier, like I'm not finished 15 minutes earlier than I did. But in the end, I have like 20 more minutes because I have one more penalty. But it's really strange. Like, see, a person solves everything in 50 minutes, he gets 200 short rank. It's very strange for ABC. I don't know, maybe like in Japan, it's common knowledge how to compute number of inversions, how to do a traveling salesman problem. But yeah, it's like really strange, really strange. Oh, I keep forgetting like that I can add myself to favorites and see the results actually. Yeah, but anyways, it's strange. Like I believe I finished earlier than in any other AtCoder contest, and I'm still like in the very uncomfortable place of 414, whereas the previous two ABCs I was like 88. That's really strange. I don't know what happened here. But yeah, as you can see, like here I spent a lot of time implementing D. I actually already forgot what D was. Ah, okay, so maybe, yeah, I was trying to explain it to make sure that I don't make anything stupid. So maybe that's why it took a bit a bit longer. Here it's, what is the difference? Like 12 minutes and 17 minutes. So maybe just a bit shorter on typing TSP, I don't know. And here I was actually pretty quick. Like if I were to have it like from the very beginning, it would like last 5 minutes were debugging that intro overflow, which was really stupid. So yeah, like I spent actually like 17 minutes on the implementing it because also because I was trying to find my submission. If I were to like, oh man, I could have finished at 55 minutes. Honestly, could have. But then again, it wouldn't bring me much further, like much closer to the front pack. So I don't know what happened here, but apparently something strange. Because for me, like, I don't know, like, if I did perfectly today, it would, like, 50 minutes is minimum that it would take me. And I actually solved this right? Mathematically, this problem faster than other people, apart from Tom, who for some reason decided not to do E. Maybe he found it annoying. I don't know. But that's strange. Like, I had a really good feeling about that contest and it turned into terrible. I don't understand how it's possible. Anyways, that's not the. This is not the topic of this video. This video was an editorial. I hope this like quick solution helped you. And I will put a link to my codes on my GitHub into the description. So yeah, I hope this helps. And with that in mind, see you later tomorrow for AtCoder. Bye bye.